Hey everybody, how's it going? Let's see. Is this a reasonable volume for the microphone? Okay, thank you. So does everybody remember this slide way back in lecture 2 where we were using Bayes' rule to calculate the likelihood of if we flipped a coin 50 times, got 33 heads, what are the odds that the coin is biased, right? This was a model-based Bayes thing where we have this idea that, hey, coins are mostly fair, but every once in a while the mint screws up and drops a 60% heads coin, right? Remember this? And there was this conversation on Campus Wire. I don't know if anybody ever saw it. But the second part of this slide was, okay, right? We calculated the probability that the coin was biased given the flips. And it was only like an 8.5% chance that the coin was biased. And step 2, the next slide, was, okay, what if we flip it another 50 coin flips and we get 29 heads? And I copy-pasted this slide out of some lecture notes from a CS class in Stanford, right? And I didn't check this, but somebody checked it. One of you was very diligent and noticed that these exponents right here, that's the 33 heads that was back here on the first set of coin flips. If you put 29 heads in here instead of 33 heads, you get a different answer, right? So one of you diligent people caught me copy-pasting somebody else's bad lecture notes. Okay, so number 1, I'm owning up to a mistake. Number 2, I want to point out to you that in the same repo that has our lecture notes, our slides, I put a notebook actually for last week, and I never got to it. This notebook has been sitting there for, 5 days now. So it's been a long time since I wanted to cover this, but I do want to show you because this is a doing class. So far we've been like all wrapped up in math and theory. I also want you to understand how to do. So here's an example of how to do. I coded up in a dumb function, binom Bayes, this same question. There is inherently a model-based approach here, right? A coin is either biased or it's not. And if it's biased, it's going to be 60% biased or whatever else we parameterize it as. So I parameterized my thing this right here. Should match up to this right here. With the idea that we want to calculate, given a certain sample of coin flips, where H is the number of heads seen in n flips, and a certain model, right? So this is the prior of biased coins, and this is the probability of heads given that a coin is biased. We assume inherently that fair coins are 0.5. So all the rest of this is just me returning the calculation that you saw here, right? So I'm not going to go through it in more detail than that. I just want you to know you can write Bayes math in Python. It's not a big surprise, but maybe an example is helpful. So when we run experiment 1, right, we get the same thing as the results on the first slide. We get an 8.5% chance of this being the biased 60% heads coin. So if we take this posterior estimate, right? We started with a prior that was, I don't know, about 1 in 100 coins are biased. It was a guesstimate, right? Well, we did the math and we got a posterior estimate. But if we do another sample on the same coin, another 50, and we get 33 heads again, well, that's when we get the value that was on the slide, right? I plugged in the output of experiment 1 as the prior this time, and that's what matches this ridiculous value here. But if, on the other hand, if our second experiment was what the slide said it was, not 33 heads for a second time in a row, but 29 heads, well, that means that the actual real value of the posterior after the second is going to be 14.5% chance of bias. Okay, again, this thing is out there for you to play with. I encourage you to play with these things. I will drop them in the repo from time to time. If I'm not too slow, we'll sometimes actually get to talk about these things. But I think some of you have had my class before, and you know sometimes I don't keep up with the lecture schedule. I encourage you to play with this, not just for the sake of understanding that one little problem, but just because, as always, playing with stuff is going to help you understand it better. Okay, but you wait, there's more. All this coin flip stuff, why are we doing it? Because it's the damn simplest version of Bayes estimation. Coin flips have one and only one parameter, the probability of heads. Other distributions, like the normal we're going to talk about at some point today, has more than one parameter, right? And every time we keep talking about Bayesian estimation, well, we're talking about, with coin flips, the probability of heads, single parameter. But we can do Bayesian estimation. I'm going to give you a little bit of foreshadowing for any parameter, mu or sigma. We can estimate any statistical parameter using Bayes. Okay? But for right now, let's stick with the coin flip because I want you to understand that beta distribution, that beta prior. That beta prior, and it's also the beta posterior because beta is just a funky exponential, right? And remember how Bayes looks. Bayes looks like prior multiplied by likelihood equals posterior. I'm going to try to do it for your version, right? So prior likelihood posterior. Well, exponential times exponential, remember that? That's just going to be another exponential where the two exponents get added together and create the new posterior distribution with an exponent that's just the sum of the exponents of the prior and the likelihood, right? That's what we covered last time. Okay, I'm going to get back into that, show you that again in a minute. But the funky thing about these betas is that they're both prior and posterior, right? Maybe it's helpful if I go say that, because I'm seeing a lot of blank looks. Remember this coin flipping example from Friday? So this here is the coin flip, right? We got 3 heads, probability of heads to the 3rd power. We got 0 tails, probability of tails to the 0th power, right? 2 exponents. But what's this prior probability? The prior probability is a beta distribution. A beta distribution has got the same format. It's exponentials. But it has this special form to the alpha, to the a minus 1, to the b minus 1. right? Well, probability of heads to the third power for the 3 heads, probability of heads to the a minus 1 power, well, just block those two together. 3 plus a minus 1. Collapse them both into one term. Likewise with the probability of tails, 1 minus the probability of heads. This is the tails probability, right? So here's the likelihood function. It's to the 0th power. Here's the beta prior. It's to the b minus 1 power. Well, it's just 0 plus b minus 1. Collapses down into a single term, right? So the posterior and the prior are the same damn thing. They're beta distributed. What are these a's and b's? Right? What are these a's and b's? Well, the thing is that an a and a b for a beta prior, you can just see them as imaginary coin flips that never happened. Okay? A is an imaginary number of heads. B is an imaginary number of tails. What is our prior belief in this coin? Okay. So, coming back over here, beta. If my imaginary coin flips that go into my prior, if I have equal numbers of heads and tails, then I think the coin is fair, right? So if I think the coin is fair, then A and B have to be the same number. Beta distributions with A and B being the same number, whatever that number is, are symmetric. Okay? And if you look at my little graph that I made, which, by the way, shows you, this whole thing shows you how to use SciPy stats beta, right? And for all of SciPy stats, whatever the distribution name is, if you call distribution name.pdf, you'll get the probability density function of the distribution. So if I pass in beta 5, I get this orange line, which is centered at fair 0.5 and pretty variable, pretty wide, right? And if I pass in beta 40, that is an imaginary, my prior is like an imaginary 40 heads and an imaginary 40 tails, I get this very sharp purple line, right? Still centered at p equal to 0.5, still symmetric, just much sharper, much stronger belief that the coin is fair, right? Orange line is like, most likely value is fair, but it could be anything. The purple line is, my prior belief is this is a fair coin, people. Okay? So, remember how I said, priors can be your beliefs, not backed up by any evidence. They can be a previous experiment that somebody did on the same coin, right? They could be something you pulled from the literature around coin flipping, right? They can be anything in between. But whatever it is, if you're encoding a fair coin, well, that beta has to have A and B equal to the same amount. And the bigger those A and Bs, the bigger your belief that this is a fair coin, the sharper the distribution. What do you notice about beta 1? How is that different? Bueller? Anybody? Yeah.
It doesn't show any likelihood.
Louder?
It doesn't show any likelihood. It's just a straight line.
It's just a straight line. What do we call that straight line? I heard somebody say uniform distribution, and that's what it is. Right? Remember, A minus 1 virtual head flips B minus 1 virtual tails. Well, 1 minus 1 is 0, right? So that's why the beta distribution at 1, 1 is a flat line. And a flat line is a uniform random distribution. This is the so-called uninformative prior. I don't know jack. Right? I don't have any virtual coin flips in my mind on my prior. So this uninformative distribution is a special case. Most distributions have an uninformative parameterization. And this is like, I don't have prior beliefs. I don't know. I'm going to assign every possibility equal weight. It's the most uninformative thing I can do, at least for a certain definition of uninformative. Okay? Well, let's see what else the beta can get to us. Well, as the ratio of heads to tails changes, right? Remember, A minus 1 heads, B minus 1 tails. So as the ratio of heads to tails gets bigger, well, the beta distribution shifts to the right. And as that ratio gets smaller, this distribution would shift to the left if you did the opposite. You should play with it. There's a few funky special cases, right? Like you'll see these distributions can get really skew when the ratio gets wacky, right? And the special case is always when one of the parameters goes to 1 or even less than 1. Okay? Beta distribution does exist for values less than 1 on the parameters. So beta gets funky when we get to those areas. But in general, for a coin flipping example, it's not particularly relevant. But just note that the beta distribution doesn't have to look like some sort of moved over normal. It can get skew shapes on it, depending upon the parameters. You should explore, right? You got a notebook. Okay. So you can do the same thing for the binomial distribution, right? And remember, the binomial distribution is our likelihood function of the coin flips, right? Product of a binomial, one for every coin flip. So if I have 3 binomials, sorry, I just said that absolutely wrong. A product of Bernoullis for every coin flip. And a sequence of coin flips is a binomial. And either way, you get the same damn parameterization. And so you can easily see that showing that likelihood function, when we have the likelihood function of a binomial of getting 3 coin flips all turning up heads, given a p-value of any possibility here from 0.5 all the way up to the brown, which is all heads all the time, right? P equal to 1. Well, which one is the highest likelihood? It's the brown line, right? The brown line has the highest likelihood. That's why the maximum likelihood estimate of seeing heads, heads, heads is P equal to 1. All right. So this is all in ways both to cement the ideas and to get you exposure to SciPy stats, right? You should absolutely play with SciPy stats if you haven't already. Understand that you can get PDFs, random variates when you need to make random draws from a beta or a Bernoulli or whatever, right? You can use the same interface. So the docs are your buddies. Any questions? I'm seeing a lot of faces going, Okay. let me finish up. So the idea of all this coin flipping, like we were talking about, is that we're after finding out what our posterior is after we acquire data, right? This, by the way, I had questions on Friday after class. It was a really good question. It was basically, what the F are we doing all this for? Right? Anybody want to answer what the F we're doing all this for? I'm going to give you two options. You pick. Number one, at some point, we're going to apply these principles to do machine learning. Number two, I'm giving you practice on things that you will have to understand if you continue to read technical literature on machine learning beyond this class. So kind of like a mini course getting you prepped for a grad school or something. Which option do you like better? I've got literally a 50-50 split on fingers I'm seeing. Right? So I think most people really prefer when there's an immediate payout and we actually apply some of this, and that'll be mostly true. Okay? That'll be mostly true. Why are we doing things like frickin' Bayes estimation? Well, hey, you've got a bunch of data points. You've got two contrasting models to explain those data points. Which model is the better model? That's machine learning right there, right? I got two potential sets of parameters for my magic machine learning system. Which one does a better job of explaining the data and predicting the data? I can use a Bayes framework for that. We're also going to get, by the way, hopefully next week, into a classic thing where we have mixtures of Gaussians, right? We have a bunch of scattered data points, and we assume they're generated by two separate Gaussians, or three separate Gaussians, or four, or whatever. How do we assign data points to Gaussians? What if the Gaussians kind of overlap? It gets really tricky. The math looks a lot like this math, okay? Now, for those of you that held up two fingers and you're like, prep me for grad school, probably some of the things that were in my pre-lecture this time we're hardly going to use. Information theory stuff, like every single thing we do in this class can be understood from an information theoretic standpoint. If you're interested in information theory, there is a 100% free textbook that is available by a guy named David Mackay, who was a researcher at Microsoft Cambridge, who wrote this brilliant textbook that just shows you how every single thing we do in this class could be recast as information theory. I recommend it when you're in grad school. Okay? So, I'm not trying to beat you over the head with stuff that doesn't matter, but it can seem like it because I'm throwing tools at you fast, fast, fast without being able to connect them to something really applications-oriented. Please keep asking me this question, okay? Because if I'm not telling you explicitly how something works, maybe it's not clear. I just assume that you can see the application because I'm at the wrong place. Okay. So, what did we learn so far today in class? I want to mention the idea, again, that this is really all the same thing. We're using the Bernoulli distribution and the beta because they're actually just fundamentally both just exponentials, right? So they are both parameterized like this, but they both, by the way, did anybody notice this? What does this little symbol mean? Yeah? Proportional to. Why did I go from equal to proportional to? I'm going to ask another person. Because there's a constant that's going away here, right? One constant that's going away is this normalization by the marginal, right? I just threw it away. But there are others, okay? There are other constants that went away. Because the difference between a Bernoulli and a beta is that they've both got different constants on the front of their, you know, to the x, theta minus 1, to the n minus x, right? That's the Bernoulli. There's some constant on the front of that I've thrown away, okay? The beta has a different constant too on the front of its a minus 1. Okay? And I threw this constant and this constant away the instant I went to a proportional, because who cares? Right? So that's why we use proportional all the time in Bayes land. And that's why we can really cleanly put these two things together without caring about what those constants are. And we don't have to try to combine those constants. If you remember my pre-lecture from Friday, I talked about the constant on the beta distribution, and it's a big pain in the ass and involves something called the gamma function. You don't have to know what a gamma function is. Throw it away. Right? So we can solve this analytically, right? I can plug this into Python, and I can graph it. Give me a set of A's and B's. Give me a set of coin flips. I can plug numbers into those parameters, and I can make a graph, right? I can solve analytically for a particular value on that graph too. So, actually, let me go back and suggest to you, right? Any one of these betas that I'm just showing you what the parameters do, you can imagine that as going from a prior distribution, like maybe that orange line is the prior, and then I gather some data, and the posterior is a new beta, maybe it's the red line, okay? Prior, gather evidence, understand what the posterior is a little bit better, a little bit sharper. Okay, that's pretty cool. That means that I can plot the posterior distribution. And what does that mean? The posterior distribution, if this red line is a posterior, this is a likelihood distribution of parameters. Bayesian estimation does not tell us this is the parameter. It says, here's the probability of the parameters. They are mostly around this one location, but you know, there's a small but finite chance that it's something else off on the tails of that red line. Okay? Does that make sense? Bayesian estimation doesn't give us one answer, it gives us a distribution. Is that clear? Isn't that funky to not get one answer, but to be offered the answer is with probability blah blah, this one. Except there is something called maximum a posteriori, or otherwise abbreviated MAP. Maximum a posteriori says, hey, you know, if this is your parameter distribution, and my posterior looks like this, maybe my prior looked like this, right? And I got some data, and I turned that blue line into the red line on the posterior. So the full Bayesian thing is just give me that red line. That's my answer. But MAP says, give me one best parameter. And the best parameter is the maximum of the posterior distribution. Clear? Okay. I want to show you something. In our example with 3 heads out of 3 flips, right? The likelihood was like this, in yellow. So our maximum likelihood is probability equal to 1. Right? 3 head flips, the most likely parameter to have given us that was p equal to 1. With any Bayesian, we take into account the prior, like we talked about, and that prior will keep us away from the MLE if the prior is informative. In the special case that our prior is the uninformative beta 1,1, we will collapse to the maximum likelihood estimate. Okay, this line here will shift over if the prior is a flat prior. Okay, in general, how do we find the maximum, the peak of a beta distribution? Well, just keep in your mind the idea of what a beta distribution is. It's a set of coin flips with A-1 heads and B-1 tails. So, the posterior, once we add in H heads for reals and T tails for reals, right? We collapse the likelihood H and T into those betas on the posterior. Well, that means that the posterior distribution of beta is H plus A-1 heads and T plus B-1 tails. Okay. So the peak is going to be the same thing as you're used to, number of heads over total number of coin flips. Number of heads is H plus A-1 now. Right? The total number of coin flips is H plus A-1 plus the tail flips, T plus B-1. Well, the 2 minus 1s become -2, right? So this is literally just combine the prior coin flips with the actual observed coin flips and the ratio of heads over total coin flips, combining those simulated prior coin flips and the real observed data. Okay. Am I going too slow or am I going too fast? I cannot tell because the stairs are relatively blank. Any questions? So remember, our posterior beta is just all the data, real, plus the simulated in your head stuff of the prior. So the parameter, H plus A-1 over all this junk here on the bottom, that's right here. That's that peak. That's the value of the parameter that gives you the maximum of that beta distribution. Now, once again, For those of you that took COGS 118A, this will be very familiar to you. Argmax is not the same thing as max. I do not care at all what the actual value here is. That's the max. Don't care. I want argmax, the value of theta that maximizes the function. Right? The value of theta that maximizes the function, well, that's why I can throw away constants. I can take any function, divide it by a constant. It's still the same shape. It's just rescaled. Throwing away constants screws up this. It does not affect the argmax. Okay. So this is where you can see that the uninformative, yeah, question.
So to clarify, this process is only for estimating the probability of heads?
Yeah, so yeah, we're estimating the probability of heads.
Okay, and so if we have like n parameters, like more than 2, then we'll be doing n minus 1 processes.
Yes, you can reparameterize it. I mean, okay. You can either do them completely separately, which is certainly the case when parameters are independent of each other, like mu and sigma, right? Or you can lump them together. Hello, linear algebra. Right?
So then the output would be like a set of mu and sigma.
Mm-hmm. Yeah.
You would have to how would you tune each one individually?
It depends on your application and lots of stuff. In general, Bayesian things are super individual. And I also, to be brutally honest, I have less experience doing Bayesian estimation than almost anything else in this class. So I know enough to know that I can screw it up. Okay, whatever. So you can work these examples yourself. You can see that putting in this prior with different A's and B's is going to lead you to make different estimates. And in the case of putting in the uninformative prior, that's where you get maximum likelihood answers, where this line here shifts over to the MLE answer. Okay? Play with this. Honestly, go to this thing and pretend that you are doing different priors and different observed data, and see how you can just draw a beta distribution or solve for this, the maximum a posteriori, and see how that answer changes with different priors and different things. Guarantee you that's on assignment 1. Literally assignment 1 is do that, so you might as well play with it now. Yeah?
On that note, when is it getting posted?
Yes, good question. When is assignment 1 getting posted? Today. So we've been working on it, and the holiday delayed us along with a technical problem. So I want you all to have assignment 1 for a full week. So I am already moving the deadline on assignment 1, which was normally supposed to have been due next Monday, to next Wednesday. Assignment 1 has already been drafted, and it will be out to you in a GitHub repo after one of my IAs gets a chance to double check our work. Okay? Yeah.
Can you explain again real quick why the denominator for the modal distributions, like h plus a plus t plus b plus d?
Yeah, I can explain it again, but before I do, are there any other assignment 1 questions? Okay. So what's going on here? Let me try to get rid of all this stuff I've been writing all over the screen for a second so that we can talk about it more cleanly. It's obviously going to take a minute. I wish there was a better tool here. Okay. So, one more time. The prior, how you interpret a beta prior, A minus 1 heads, B minus 1 tails. Remember that the posterior is also going to be beta distributed, but the posterior is going to have the A minus 1 prior coin flips plus the actual observed H coin flips, right? All good? Likewise over here, the actual observed tails and the prior tails, the B minus 1 priors. So, whatever the shape of this distribution generated by these parameters, where is its peak going to be? The peak is going to be, because again, remind yourself, this is just like any other Bernoulli or beta or whatever. Like the representation here is that this is the probability of heads, right? Theta to this power is the probability of heads. So we only got two options, heads, not heads, right? So where does the peak of this distribution lie? It's got to lie at the number of heads over the total number of coin flips. Because again, this is really just a fancy Bernoulli, right? Where this is the probability of heads and this is the probability of tails. So this over the two exponents put together is the number of heads over the total number of coin flips, both virtual and real. And that's got to be where the peak of this distribution lies. This is the intuition. You could actually do the frickin' calculus and take this and derive it and set it equal to 0 and then solve, and you'll get this answer. But I'm giving you the intuition. Does that make sense? Yeah. The usual thing. You want to do this analytically, derive your thing, set it equal to 0, solve for the parameter. Okay. So, woof, I blew away the whole class without actually getting to normal distribution. But should we do normal distributions? Are you ready? Okay. So, the thing about normals is they're also exponentials. They're from the same family as Bernoulli and beta. Bet you never realized that. Right? What is a normal distribution? We know what it looks like as shape. You're way familiar with that, but remind yourself of the math. Exponent, in this case, it's the natural e, right, to the power of something, right? So, but this is an exponential. It's in the same exponential family. Okay, some things that you probably already knew in the dim recesses of your mind, but I want to remind you about. Why do we call it the normal distribution? It's because when you take a bunch of random variables and add them together, as long as those random variables are statistically independent, you have to get a normal distribution in the limit as you add more and more random variables together. Okay? I don't care if all those random variables are wacky, wacky shit. If they're Poisson or hypergeometric or whatever funky distribution you don't actually know what it means, if you add together enough statistically independent random variables, the result of that sum of random variables is a normal. This is the so-called central limit theorem. Now, lots of real-world processes are a bunch of factors combining together to make one thing you're measuring. Human height is not determined by one gene. There are lots and lots of little genetic switches, plus a lot of shit that happens in your environment, like the nutrition you get when you're a kid, they're all at least close to independent of each other in the process. That is why human height is normally distributed. That is why so many things in the real world are normally distributed, because most things that matter are not one thing, but lots of things interacting. Right? So, normals are great because they're exponential family, which makes the analytic math easy. Right? They've got some interesting properties, like if you remember when we talked about entropy in the pre-lecture, for a given mean and standard deviation, a normal distribution is the maximum entropy you can get. Other distributions will have less entropy. Pop quiz, what does it mean to have a high entropy? Yeah? Sorry, I couldn't hear.
Distributions are not separable?
They're not separable. That's not quite what I mean. Is there another alternative?
There are more ways to arrange things in the system?
There are more ways to arrange things. That's a little bit closer to the usual meaning of entropy, right? So think about it like this. Entropy equals surprise. Before I grab a sample from the random variable, how surprised am I going to be on the outcome? If my coin is always going to turn up heads, I have no surprise. I don't have to do the experiment, right? I know before the coin flip what the outcome is going to be. That's low entropy. It is a highly ordered system. If you're a physicist and you know entropy from thermodynamics, right? High entropy systems are highly disordered. Low entropy systems are highly ordered. The most ordered thing is to know the outcome before I draw the sample. Okay? Coin flips only have two outcomes. I don't care, right? Like, that's pretty easy. I can guess it's going to be right 50-50 if it's a half coin. It's not a very high entropy. Normal distributions are on a continuous basis, so they've got more possible outcomes than coin flips. In addition, the nature of the big long tails on a normal, right, going way out here, mean even crazy values will turn up from time to time way out here in the tails. So the outcome of a given draw from a normal is the highest entropy we can do with a given mean and standard deviation. Okay? All right, so let's take a moment with the idea of the normal. Let me make sure I got my time okay. Okay, I can do this. So let's look here. What is this term? Actually, let's start here in green. For a given data point, x, how far away is it from the mean? Right? This is the mean of my distribution, right? If I draw a data point out here, what's the distance from that? Okay. By the way, it's squared. Distance squared, so negative distances and positive distances, it doesn't matter. Once you square them, they're the same number, right? So I don't care about whether I'm on one side or the other side of the mean. The square gets rid of negative sign issues. So all we care about is raw distance. Now it's normalized by that sigma. So what's sigma? Sigma is standard deviation. And what it does is it means that whatever that value is for standard deviation, right? What we've got is this number is in terms of how many standard deviations away I am. At 1 standard deviation away, or at 2 standard deviations away, or at 3 standard deviations away. It doesn't matter what the standard deviation number is. I'm normalizing it to be in terms of how many standard deviations away from the mean am I. Okay? Is that clear? So this exponential fall off that we see here, this is the exponential, right? That exponential is parameterized in terms of how many standard deviations away am I. So the nature of a normal distribution that you should always keep in mind, and again, I'm probably telling you things you've known since high school, plus or minus 1 standard deviation around a mean, you get 68% of the probability mass, right? And 2 standard deviations, you get 95% of the probability mass. And at 3 standard deviations, you get 99% of the probability mass. That shit's just math, okay? So now that we've got all the basics of a normal distribution out of the way, of course, we've finished. And next time we'll talk about more complex things, okay? Hey, what's up?
My friend wanted me to ask you, he couldn't come here in person. He wanted me to ask you about the wait list.
Oh God, I forgot to say about the wait list. As your way out, the wait list is getting completely resolved. Everybody on wait list will get in. They gave me another TA.
Thank you.
Yeah.